Good afternoon, the participants and the organizer of the Climate Resilience Agriculture for Asia 18th TSAE International Conference. In this part, I'm going to talk about CFD modeling of latent heat energy storage system with cylindrical PCM capsules. Let's turn to the introduction. In the introduction part, we have analyzed the number of publications, the number of publications by universities, the number of publications by authors. And we have analyzed the different types of thermal energy storage system by energy side. As you can see in the first graph, the number of publications uh, related to the thermal energy storage system is growing rapidly, growing significantly between the 2013 to 2024. As you can see, the China has the major contribution for the development of the thermal energy storage system, and as you can see you can see the number of publications by universities in the second one. You can see also the main authors who contributed, uh, who has a great contribution for the development of the thermal energy storage system. You can see Luisa Capeza is located in the fourth place. Thermal energy storage system is divided into the three parts. The classification: sensible heat storage, latent heat storage, thermochemical heat storage. The storage medium for the sensible heat storage can be liquid or solid. For the latent heat storage system, the storage medium can be solid to the liquid, liquid to the gas, solid to the solid, solid to the gas. However, in the thermochemical heat storage system, the storage medium can be liquid to the gas, gas to the gas, solid to the gas. In order to store 6.7 gigajoule energy in the sensible heat storage system, we need 34 cubic meter, and in order to store this energy in the latent heat storage system, you can see that we should have a 20 cubic meter. However, in order to store this energy in the thermochemical heat storage system, we need 1 cubic meter. By analyzing that the thermochemical heat storage system requiring less storage volume compared to the latent heat and sensible heat storage system. However, the construction of the thermochemical heat storage system is very expensive, and also operation of the thermochemical heat storage system is very complex compared to the sensible and latent heat storage system. They require more costs compared to the other thermal energy storage system. That's why we are focusing on the latent heat energy storage system in our study. And you can see also operating temperature range of this thermal energy storage system. Let's turn into the system description, boundary condition, and method. A design of latent heat energy storage system with PCM capsules is demonstrated in the figure 1. And we have built this system in the 2D geometry in COMSOL multiphysics software. Water is used as a heat transfer fluid. Paraffin wax is selected as a storage medium in our study, and the height of the system is 1.6 meter. Inlet and outlet diameter of the tubes are 0.2 meter, and diameter of the cylindrical PCM capsules is 0.04 meter. And we have, the COMSOL multiphysics use the finite element method to solve the two-dimensional Navier-Stokes equation with energy equation. Finite element analysis is numerical computational method used in the engineering and scientific research to model and analyze complex physics processes. The finite element method is widely used to solve the differential equation to analyze the environment with the complex geometries. Boundary conditions are applied to all materials which are provided in the table 1. And the material properties which are used for thermal energy storage unit in our study has demonstrated in the table 1. And in the next page of the presentation you can see the equation and mathematics which are used in our study. And all these equations are inserted to the variable part of the COMSOL multiphysics to demonstrate the main parameters like temperature variation and the total stored energy, melting fraction of the storage medium. And in the next page of the presentation we have demonstrated the charging simulation in our study. As you can see, the temperature is increasing over the 5 hours and reached to the 350 Kelvin maximum. And in the B1 you can see melting fraction of the PCM over 5 hours. At 5 hours the major part of the PCM has transferred into the liquid. And in the line graphs you can see temperature variation of the PCM at 3 different points, T1, T2 and T3. And we have also the inlet point and outlet point temperatures. And we have also demonstrated the total stored energy at 3 different points in the next graph. And we have also conducted discharging simulation over 5 hours. And in the discharging part, the initial temperature was selected at around 350 Kelvin, and the inlet temperature was about 20 degrees C. As you can see, the temperature of the storage medium is decreasing by hours. And also melting, you can see the fraction of the PCM during the discharging period. You can see at around 5 hours the great part of the PCM has transferred into the solid. And in the line graph you can see the temperature variation of the PCM at 5 different points. In conclusion, a numerical model of PCM-based latent heat energy storage system is modeled in COMSOL multiphysics. Temperature variation of heat transfer fluid storage medium are investigated at 5 various points of the storage system. Furthermore, stored energy is evaluated by applying the mathematical expression to the variable part of the COMSOL multiphysics. From this analysis, the maximum value of the storage energy at T1 and T2 points were about 90,000 kilojoule. During the discharging period, outlet temperature of the latent heat energy storage system is decreased 350 Kelvin at the end of the time, which makes it suitable for domestic application. Thanks for your attention.